Okay, good morning, everybody. Today I shall continue on chapter 7. Just a quick recap on last lecture. What we did last lecture, we started talking about the application of a flow system here, and I did like a flow chart showing what are the topics that we are going to cover in this chapter. If you remember, under the piping system or under the duct flow, we had a piping system, we have a nozzle, and we have throttling valve. The three things under duct flow. Now, last lecture we already discussed the nozzle. Before I start the lecture, can I just make sure that you can all see the PowerPoint slides? Can you see them? Yes? Okay, great. So, the nozzle, we said the main change that takes place in the nozzle is that because of the change in the cross-section area, we do have the enthalpy converted to kinetic energy in the nozzle, and this is what we explained last time. My voice is not clear. Okay. Okay, let me just double check. How is it now? Better now, Muhammad? Is the voice better now? Okay, let me just check. All right. Okay, I may, in this case, let me just make sure. The connection is not bad. It's quite good. All right. Okay, I'll bring my mobile just to connect it. Maybe my mobile network is stronger, just in case. 1 minute. Great now. Okay, good. Is it okay now? Mariam said it's good. Is it okay, guys? All right. Okay. Then in this case, let me just proceed. All right. So as I said, with the enthalpy, with the nozzle, the enthalpy is converted to kinetic energy. Now, last lecture, I came up with the simplification of the first law of thermodynamics with you, and I mentioned the continuity equation as well. The thing which I did not start, of course, I took a special case, which was what if I have ideal gas, and that ideal gas was at reversible adiabatic condition. In other words, it's at asentropic. And to have this, I just integrated that equation, and I told you last lecture that upon substituting of V or replacing V with constant over P all to power 1 over gamma, according to what we have here, then you can integrate and get this equation. I hope you managed to get this equation easily, because I asked you to try it. So if you have any question, you can ask. Are you okay with that equation so that I can proceed? Yes? Hello? You okay with that equation? Okay, great. Okay, the other special case we are going to talk about today is something called the throat. Now, with the nozzle, the way you look at the nozzle, the shape of drawing the nozzle, we agreed last lecture that the nozzle is drawn as a tapered shape where the inlet, outlet are drawn like that. Now, the throat is simply this area. If you can just imagine your throat, البلعوم, it's exactly the same. Here at the throat, if you can just imagine when you eat, things get stuck in this region. And here, because of that, we call it a critical location. So with the nozzle, it's the same. At the throat, we call it a critical location. And we have the pressure and the velocity in that throat called as critical pressure and critical velocity. There are equations to be used only at the critical location. The first one is for the velocity at the critical location. The other one is for the pressure at the critical location. But those two equations are only based on having ideal gas and asentropic condition, because it's continuation on the previous slide. Okay, it is ideal gas, asentropic condition, remember. And to find the pressure at the At the throat, you have to use this relationship, which is as a ratio between final and initial pressure. Final means the pressure at the throat to the pressure. Of course, the derivation is there in your book, but just for simplification, you can just apply those equations directly. And if you can see in the equations here, it's based on the assumption that the specific heat capacities are constants, and that's why you can just directly take gamma and substitute. Okay, a very simple direct substitution in those two equations and on the nozzles equations are available here. So what I will do in example 7.2 is just to apply what we covered on the nozzle. Another thing I want to mention is that equation is based on having velocity u1 equal to 0. Normally we put this assumption if the initial velocity is much smaller than the final velocity, and that is normal case with nozzle unless they mention in the question how much is the initial velocity, or they give us information to calculate the initial velocity. Okay. Let's see what we have in this question. Here we have a nozzle, example 7.2. We have a nozzle, and in that nozzle we have been given that it is high velocity nozzle. It's designed to operate with steam. So I know that my species here, or the fluid, is steam. That steam enters or gets in at at a pressure of 700 kilopascal and at a temperature of 300 degrees C. So those are the given information. Actually, when you go and figure out the phase here, you will notice that it is superheated steam. Okay. Now, what it says, at that inlet temperature and pressure, the velocity is also given, and that velocity is 30 meters per second. Now, what they ask for, they ask for calculating the ratio A over A1. And what do they mean by A over A1? A is not the exact, here A is, طبعا A1 is the inlet cross-section area, that's fine. But A is the cross-section area at different locations. يعني, they may have asked for cross-section area at different locations. Now remember, here is the throat, and then I would have, this is called here, I call it converging and then diverging again. Then it will get into the pipe. This is what's happening in the nozzle. So they were asking for the pressure at different locations. The initial pressure is 700, and you all know that with the nozzle, we get increase in the velocity and the pressure decreases. So if the inlet is 700, maybe with time we may get, for example, 600 kilopascal in this first green line, and then maybe 400 in that line. I'm just giving examples. 300 maybe just after the throat. Why I'm showing this? Because it's just like they are asking to solve the problem more than once. More than once means once when the outlet pressure is 600 kilopascal, then at 400, then at 300, and so on. Of course, we will not give such a question. We will not give a question in assessment where we ask you to solve it several times. But why I changed the pressure here several times, because I want to show you an important message out of this example. And let's consider that they only ask for it as a pressure of 600. يعني, the question here is basically solving a nozzle problem as simple as normal nozzle problem, where the initial temperature is 700 and the final pressure is 600 kilopascal. And 600 might not be at the outlet, but at this location. And they were asking for the A ratio between that location and the inlet. This is basically the idea. طبعا, if you applied the first law of thermodynamics, you all know that kinetic energy is there, potential energy can be cancelled out, and Q is not there because they did not mention anything related to the heat, no work is there. So this is basically the equation which we derived already previously. So that's basically the equation. الحين, if I just check what I have in the question, I do have T1, I do have P1, then I don't have any problem with H1 because the enthalpy can be easily found from the appendix. And the point is, how to get the velocity, I don't have it. U1, I will consider it 0. Why? And here, well, maybe I have to clarify this a bit more. According to the question, this is what I have to calculate. And I don't have H, I don't have U, okay? U1, normally if it's not given and it's much smaller than the initial velocity, then we cancel it. And in the question, how can I solve this if I have only one equation? Of course, I will not be able to do so. That's why I brought the continuity equation, which says m dot 1 is equal to m dot 2. And m dot 1 is simply rho into v dot equal to, rho 1, v dot 1 equal to rho 2, v dot 2. And I already explained before that rho, it is 1 over specific volume, and v dot is the cross-section area into the velocity at the inlet. So in this case, I would have, let me just write it here. I would have A1 U1 over V1, which is the specific volume, equal to A2 U2 over V2. Is it, Doctor, why you did this? Because this will relate the velocity with the cross-sectional area. Now remember in the question, they ask for the A ratio. I can't find the A ratio without this equation. In other words, from the first equation, you should find U. From the second equation, you will substitute in that to find the A ratio. And then, Doctor, how can I solve from the first equation? In the first equation, I do have H1 because T1 and P1 are well defined. How to find H here so that U2 or U can be calculated is simply because since at the initial condition you have T1 and P1 and it is a reversible adiabatic process, mean delta S is equal to 0, mean S at the final is equal to S initial. And in this case, at the outlet here or at 600, you will be having the pressure, which is 600 kilopascal, and you will have the entropy, which is equal to S1. So now you have two properties, you can find H. So the idea is substitute in the first equation to find U, and keep in mind that both H1 and H can be found. H1 can be found because T1 and P1 are given. H can be found because once you get S at inlet, it's equal to S at outlet. So you have two properties at outlet in this case, which is 600 kilopascal and the entropy. So that's basically the idea. You can stay at home, spend some time, practice this. But I want to show you what I did. All I did here is just I combined those two equations together, which you don't have to do it. You don't have. What I did, I substituted of the given information. I left H changes because it changes based on the change in pressure. Remember, I will solve this problem more than once. Once at 600 kilopascal, another time at 600, and so on. 300, 400, and so on. So that's why I just put all the information apart from H. And once I know H, I will get U. Then after getting U, I will substitute in the A ratio equation. So basically I have two equations. Then at each pressure, I will go to the table and find at that pressure and this entropy how much I will get the H. And if you notice from the second equation, I also need the specific volume. Okay. Here they use V. That V is actually the specific volume, which I used to term it as this. Okay, so that one is specific volume, just for you not to get confused. Okay, because of that, at the outlet or at 600 kilopascal, I would need to get H and V at those two given information, which is the pressure and entropy. And then, before I show you the table of calculation, is the idea clear? The idea of applying first law thermodynamic and continuity equation to solve this question. Is the idea clear? If I see yes, then I will carry on. Yes, clear? Okay, great. Okay, wonderful. So, and because of that, what I did here, I just solved the problem several times at different pressures. Here, as you can see, I started with 700, which is the inlet, and then 600, 500, 400, 300, and 200. Remember, we need to find the A ratio, and to get the A ratio, this is the equation I have to use. But before getting A ratio, I cannot get A ratio unless I know this velocity. And to get that velocity, I already put the equation that I need, at which, by changing the pressure, that H value will change. And because of that, the velocity will change accordingly. And then, Doctora, what do you want to tell? What's the message? I want you to say what's happening before and after the throat. Let's see. And if you can just imagine, this is our nozzle. remember, this chapter is just make us very close to the processes, to the units. We need to understand what's going on. So we started with 700. The velocity was 30 meter per second. I hope you can clearly see that the velocity can get increased with time. And this is we agreed on, because the decrease in the enthalpy causes increase in the velocity. Maybe I would put it like this, just to show that the velocity increases. And this is one thing we agreed on when we describe what the nozzle is. But let's talk about the cross-sectional area. You can see there, the cross-section area, the ratio decreases. Decreases means what? A2 is smaller than A1 with time. And that ratio, you can see there, gets smaller and smaller and smaller. But it reached a place, look at that here. When it was 400 kilopascal, I was there. But when it was 300 kilopascal, the ratio get just increased. In other words, I shifted to another region, and that region is what? Is the diverge. Okay, diverge means I got increased back again in the area, so that I can just be connected to the pipe once again. So this means that the 300 kilopascal is just after the throat, because the throat is the critical location where I got the minimum cross-section area. Then it will get, you can see there, 0.088, then 0.091, then 0.104, it gets increasing. Increasing means I got to diverge once again. So this is the message I want to mention. I want to mention something very important here, which is in that location, which is between 300 and 400 kilopascal, I do have the throat. And remember, this question was covering real data of steam. What if I told you it's ideal gas? If I said it's ideal gas, then at the throat, you can use those two equations. I can find how much is the velocity at the throat. Here from the table, the velocity at the throat, it is between, you can see it's between 500 and 600, but I don't know exactly how much. All right, but if it is ideal gas, I can specify exactly the value, and this is what I did here in this example. In example 7.3, I'm just repeating, solving example 7.2, but trying to find what is the critical pressure ratio, which is P2 over P1 at the critical location, and what is the velocity at the throat. In other words, I just want to show you that I can apply those two equations, U2 squared to find the critical velocity, and the P ratio to find the critical pressure. And then 7.3 is just simply direct substitution. What they did in the question, Smith, he did not put the information here, but he put it inside the solution, which is the value of gamma, it's 1.3. He need to mention that it is reversible adiabatic. He need to mention that this one is constant value. He need to mention that it's ideal gas, because if those information are not there, then he cannot solve. Ideal gas, he mentioned it, but he did not mention the fact that it is reversible adiabatic and the gamma is constant. And upon just direct substitution, he got the P ratio, and also to find the velocity, actually you do have the equation here to find the velocity, but in the question, and you can substitute here, but what they did here in the question, to find the velocity, we substituted in the equation that we derived last lecture, or that I asked you to derive last lecture. Why is this? Because in the question, I do have the initial pressure, but I don't have, I do have the initial pressure. I do have the pressure ratio that I found based on the critical location. The specific volume at inlet 1, I do have it, so I can substitute. The problem with this equation here is that you need the specific volume at the outlet, which you don't have it. So that's why I cannot substitute in this, but I can substitute into there. Right? This equation is applicable whether it's at the throat or at a location that's not at the throat. So that's why you can just substitute in that equation directly. I don't want to spend lots of time in substituting, but let me just clarify. In the question, they give you the pressure here, which was 700 kilopascal, the specific volume. Now remember, you don't have a specific volume. You cannot go and find it from the table, because what I'm asking here, I'm saying consider it ideal gas. So in other words, what's given in the question is only the pressure P1 when you go, it's P1 and T1. These are the given information. It was 300 kilopascal, 300 Kelvin, as you remember, and 700 kilopascal. So V1 also, I don't have it, but what I did here is this. You can just substitute PV equal to nRT and find the specific volume. That's one option. Or I just found PV as one full term, because PV is equal to RT. If I divided it by the molecular weight, I will get the unit in meters squared per second squared. And then, Doctora, do I have to do the same? No, you don't have. You can substitute PV equal to RT, find the specific volume, and then substitute here, because that one is a specific volume. Okay? But the reason why I did all that in one step, because I know here, let me just clarify that. I know here from this question that this term is in meters squared per second square. So that in meters squared per second square. This term has no unit because it's a ratio. So in other words, that whole term is supposed to be in meters squared per second square. In other words, the PV term is supposed to be in meters squared per second square. For that reason here, once we get it, we had to divide it by the molecular weight so that we can get it in meters squared per second squared. But you don't have to follow exactly the same procedure. Actually, when you start solving, you will notice, and if you can, if I were you, I can also do this. I can just say PV equal to RT. I have P1, I have T1, I have R, I can find this specific volume, which is V1. Once I get the specific volume, then I can come here and substitute. I do have pressure and I do have the volume, and I can substitute. Simple, easy. And this will allow me to get the velocity. طبعا the second part, I don't like to cross anything, but as I said, if you have this circle, gray circle, then it means that will not be covered in this chapter. Zin, what is the final message you want to say about this? If I considered ideal gas, you notice that the critical location was when the pressure P2 is almost 55% of P1. That is if it is ideal gas. This is the critical location. يعني almost half of it. Half of it. Half of it means 55% of the 700. يعني around what? Around 350, 360. Okay? So that if it is ideal gas. In the previous problem, when it was not ideal, it was actual. Where was the pressure? It was between 300 and 400. يعني assuming ideal gas may be okay because it's between 300 and 400, and our critical was there from the ideal gas scenario. It was around 360 or 370, which is in between 300 and 400. You can see there. I just want you to have this engineering sense. And with regards to the velocity, the calculation says that the velocity here is 544.35. So let's see there. 533, it is between 523 and 633. You can see? So, and in other words, using the ideal gas equation can allows us to calculate exact location of the velocity and pressure, exact values. Here with the real, I can see here that it is in between. يعني I cannot say that the interpolation will be a good option here to estimate, but يعني it can be a rough estimation that is in between those two values. Okay, so that's regarding the nozzle. Before I proceed, anybody has any question on the nozzle? Because I have to shift to another unit now. Nozzle is clear? Idea of nozzle, application, the special cases that we covered in the nozzle. Clear? Okay, since I saw couples of clear written for me in the post, then I would just carry on. As I said, again, I would remind you that this means that you can just skip it in the future. You may need it, so that's why I don't prefer to delete the content. All right, back again to the flow chart. I'm not going to draw the flow chart once again, but the schematic diagram or the chart I mentioned at the beginning of this chapter shows that under the duct flow, we have three main devices. One of them is the piping system, the other one is the nozzle, and the third one is the throttling process. Now, this is the last one under the duct flow. With the throttling process, from previous chapters, all we did about nozzle is this. But remember, that is only correct, that H is equal to 0, it's only correct if you have no change in kinetic energy, no change in potential energy, no work, no heat transfer. And that's almost true generally, unless in the question they mentioned other than this. But what's the throttling? What it does for us in real life? The main result of the throttling process is that it causes a pressure drop. Then, if you have a throttling process, you get pressure drop in the system. And then, شنو يعني throttling? What kind of throttling you have? Throttling can be achieved, or you do have throttling whenever you are including in your piping system restrictions. And when I say restrictions means in the piping system you are putting things like this. And then that restriction can be orifice. And if you remember with the orifice, I think we mentioned that in Chenge Trouble 1 when we talked about measuring the flow. With the orifice here, you do have the orifice, they put it in the middle of the channel or of the pipe so that you want to measure the flow rate. And how to measure the flow rate is because of the pressure drop that takes place in the system. So you can have, as I said, either orifice, and I will remind you from Chenge Trouble 1, we have several types of orifices. For example, it's ring type, it is disc type, but it's something that they put in the middle of the channel while the fluid is passing through so that it causes the pressure drop. The orifice, we know why they put the orifice, because they want to measure the flow rate. It can be that we put a closed valve or partially closed valve. I put a valve here that can be partially open or partially closed to control the flow in the pipe. So that is also a throttling process. It can be that we put porous black. Porous black means it's kind of a membrane or sieves or sheets at which, for example, with water treatment, they put such kind of membranes to treat the water, removing the particles from water. Okay, so such kind of restrictions, when you put it in the piping system, you go to pressure drop in the system. And then it can also be capillary tube. With the capillary tube, somebody will say, Dr. Enzin, there's no restriction inside the pipe. Well, actually, that is a lecture by its own. But briefly, with the capillary tube, you have something called, because of the friction and moment of inertia here, you got the fluid, it's restricted because of having a narrow pipe, and its interaction with the wall causes a pressure drop to take place. So that's why with the capillary tube, you do have pressure drop, and that is kind of throttling as well. So those are different types of throttling processes. And in all those types, what you get is basically reduction in pressure because of having those devices or parts fed in the piping system. So at least by now we understood the throttling process compared to before, at which we only said it's delta H equal to 0. And here, after we understood what's the throttling process, now to talk about the first law of thermodynamics, you all know that generally there's no work, no heat transfer, no change in the kinetic energy, no change in the potential energy, and for that reason delta H is equal to 0. زين الحين what does delta H equal to 0 means? Again, all what we covered before is that if it is ideal gas, which is the special case, if delta H is equal to 0, then H is a function of temperature only, then T1 equal to T2. But my question here, will it always T1 is equal to T2? Or is there chances that the temperature will decrease or increase in the throttling process? So the answer is, it really depends on the nature of the fluid. And with ideal gas, we have no problem. We already said, it was clear before, that with ideal gas, it's only function of temperature only. It means, in all that here, delta H is equal to 0. But does this mean that T1 is equal to T2? As we said, it depends on the nature of the fluid. And with ideal gas, as it's mentioned here, with ideal gas, yes, if you have delta H is equal to 0, then there's no change in temperature. And we already know that before. Now, with regard to real gases, actually, if you have moderate condition of temperature and pressure, then normally the change in when delta H is equal to 0, the reduction in pressure at constant enthalpy will result in reduction in temperature. In other words, if delta H is equal to 0, and the pressure decreases, which is the case in throttling process, because in throttling process, it's always that the pressure will get lower. So in other words, if delta H is equal to 0 and you have real gases, then reduction in pressure will lead to reduction in temperature. So the answer is temperature will decrease if you have real gases. You see, that is with regards to real gases. With regards to what if you have saturated mixture, it's not It's not real gas. It's saturated mixture. يعني it is wet steam. What I did here for you, I give an example. Why I give an example? Because I want you to try yourself and see what will happen if you have saturated mixture. شنو يعني دكتورة? What do you mean? I meant if I have a throttling process, okay, for example here I have a bulb, and I told you that the inlet you have it as saturated mixture, and I give you, for example, the temperature. Of course, if it is saturated mixture, I need to give you the quality. If I did not give you the quality, you won't be able to solve. Remember that. Either the quality or information to help me calculating the quality. Easy. If I give you it is saturated mixture at the inlet, and then I told you, for example, that the pressure, pressure here P2 is equal to, and I give you the value of the pressure. And I know that the pressure will decrease. Then I ask you, will calculate the temperature. And if I ask you to calculate the temperature, means I'm asking you to see whether the temperature will decrease or increase. And remember, in the previous slide, we had a rule about the ideal gas, and we said temperature will not change in throttling process. We had another rule about real gases at moderate pressure, and we said that the temperature decreases in the throttling valve or throttling process. Here I'm talking about saturated mixture. It says here, when you throttle, now in the throttling device, the process we call it throttle, or sometimes you will notice also another term that they call it flash. Yani they put the stream in and it flashes. Flashes means the throttling process take place there. So throttle, flashes, those are terms used for throttling process. Zin. So what we have here, we have throttling of wet stream. طبعا if I put the wet steam in, يعني the saturated mixture fluid, I put it in, and I want to reduce the pressure. And just imagine with me, you have a fluid, it is mixture, and you are reducing the pressure. طبعا with the reduction in the pressure, okay, it means you are allowing the molecules to be far away from each other. يعني the liquid itself inside the mixture will start to evaporate, to be vapor. It can be converted from saturated liquid to saturated vapor, or from saturated mixture to saturated vapor, or from saturated mixture to even superheat. And this, because the more the pressure is saying, the more is the shaft towards the superheated vapor. But will the temperature decrease or increase? Here is the question. Okay, so what I did, I give you an example here, which says that the inlet saturated mixture is given at a pressure of 1000 kilopascal. And I can either give you the pressure or the temperature because it is saturated. If I give you the pressure, you can find the saturated temperature from the table. I don't have to give you both. But what is really important is to give you the quality at the inlet because it's saturated mixture. So this is what we have in the question. It is throttled so that the final pressure is much lower than the initial pressure, of course, because this is what's happening in the throttling process, and it's only 101 kilopascal. So the pressure reduced from 1000 kilopascal to what? To 101 kilopascal. And here they were asking for the temperature. So how to solve? I'm not going to solve the problem. I'm just putting this as an example for you to prove what will happen. And I can tell you the conclusion. Temperature will decrease. But how to calculate this or how to give a proof for this? This is a throttling process. The delta H is equal to 0. In other words, at this T1 and X, it is saturated mixture. You should be able to substitute in that equation. Delta H is equal to 0 means H1 is equal to H2. And this is the common thing between inlet and outlet. If I do have the quality, means that I can go to table either F1 or table F2. But what will I do? I will just substitute to get H1. H1 is equal to H liquid plus X HLV or delta HLV. And quality is already given. H liquid and HLV, you will find them at the given. Here you have both temperature and pressure. But if you use table F1, then you will need the temperature mainly. If you use table F2, you will need the pressure. My suggestion is that you have to use table F2 because the pressure is 1000 kilopascal and it's there. Rather than using fractions of temperatures and because you have temperatures that is 0.88, then you may need interpolation in table F1. So again, I will repeat, you will go to table, here, you will get to table F2 at a pressure P1 is equal to 1000 kilopascal. You will get the saturated properties. Saturated properties means you will get H liquid, you will get H vapor, and then you will substitute in the H, which says H is equal to HL plus quality HLV. Okay, and how to get the saturated properties? It is from the first two columns of table F2. زين طبعا once you get H1 and you know the relationship between H1 and H2, then the final state is well defined, because at P2 and H2 you can find how much is the temperature, and you will notice that the temperature is less than T1. خلاص? So that is the conclusion number 3. If you have saturated mixture and it is throttled, then again the temperature will get lower. A fourth case. What if I have saturated liquid? Not saturated mixture, saturated liquid. The procedures are exactly the same, and you will also notice that temperature will be lower than T1. And I'll give you here an example. So what's happening here is that at the inlet of the throttling process, it is saturated liquid, and you will notice that upon lowering the pressure in the throttle, you are lowering the pressure in the throttle, then that saturated liquid will start evaporate because we are reducing the pressure. Or flashes, as I said, you can just use throttled or flashes or evaporate, and when it is saturated liquid started to evaporate, then you would have mixture of saturated liquid and saturated vapor. خلاص? This is what would happen. And as I said, temperature will decrease. And that example shows the case. You can just solve it exactly same as what I did in the previous slide. I'm not here asking you to solve, but just if you want to get a proof, it's a practice for you, but you can just get a proof to know what's happening. Okay, so conclusion with the throttling process, it's a device at which you have restriction in the piping system, and because of that restriction, you get a reduction in the pressure. And with the throttling process, delta H is equal to 0, but what this delta H equal to 0 means depends on whether you have ideal gas, real gas, saturated mixture, saturated vapor in the system. And in all cases, apart from the ideal gas, the temperature gets lowered upon reduction in pressure. But with the ideal gas, the temperature will not change. This is the summary of the throttling process. Anyone has any question on the throttling process before I move? Clear? Clear? Yes? Hello? Okay, great. Here, this is the last thing I want to show about the throttling process. Actually, I don't want you to solve this example. This example, I want to comment on it rather than to solve it. Here I have propane gas. And remember that's propane, that is not steam. The initial pressure was given and the initial temperature was given. It says that it is throttled. I have it passed through a throttling device. But the point here is what? Is the pressure get decreased from 20 bar to 1 bar. And they were asking how much is the final temperature. Question number 1. Can I go and use the steam table? Of course I cannot, because I have propane. And when I say delta H is equal to 0, and then I say H1 is equal to H2, yes, I do have P1 and T1, but I cannot go and get H1 from the steam table because I have propane. Did they mention in the question that it is ideal gas so that I can use the ideal gas equation? No, they did not. But what they did, they said properties of propane can be found from generalized correlation. What is this? Generalized correlation, it is what we did in chapter 3 about real gases and the correlations. But that will only be covered in Cheng 212. Director, why you are giving us such a question here? I'm giving this question just to show you that what if I replace this by saying it's ideal gas? And you all know that if it is ideal gas, the delta H is equal to 0, H is a function of temperature only, then T1 is equal to T2. Is this what they want in the question? No, what they want in the question, they want me to calculate the entropy change. Look, the entropy change. But I have no problem, and if I know that the temperature will not change and it's ideal gas, entropy change is simply Cp ln T2 over T1 minus R ln P2 over P1. طبعا that term will be cancelled out because the temperature is not changing. And here it's only R ln P2 over P1, and that's why I did the calculation here straightforward and I got the value of entropy change. Okay, so entropy change, I have it. So that's wonderful, but this is only if it is ideal gas, and temperature will not change. In your textbook, they solve it using the correlation, which is Ching 212. I'll just write here next to it Ching 212, okay? But I just want to draw your attention that if they use the correlation, they put the temperature as 385. There is a difference between the ideal gas and real gas calculation. And entropy change, they got it as 23.8 joule per mole Kelvin. I got it as 24.9 joule per mole Kelvin. Now the deviation is around 3 to 4% with respect to T and with respect to S, which sometimes the assumption, it just tells me here that assumption of ideal gas can be accepted. And this is what we did here. We accepted the ideal gas assumption in our work. Okay, and 3-4% as an error could be accepted. Okay, so this is the only message I want to mention in this. With that, I announce the end of this lecture. Anyone has any question before we close the lecture today? So next lecture we will cover other devices. Clear? Clear, guys? Hello? Okay, wonderful. If that's clear, then I will have to stop the lecture now and see you on Tuesday.